Bergstrom here to talk about liberating effects with rows and handlers. There we go.
Yes,
Great.
Thank you, Richard. Yeah, so I'm Daniel. Here to talk about my work on liberating effects with rows and handlers, and it's joint work with my advisor Sam Lindley. So what exactly are we liberating effects from? Order, and how are we doing that with rows and handlers, hence the title. So just to put it in a little bit of context here, just scale this down a bit. I will scale it up in a moment. Just want to put it in a context here. Monads has been sort of I think it's fair to say, the de facto way of handling and controlling computational effects in at least functional programming. And rightly so, has been a very successful approach to this, but it also well known that you cannot expect two monadic computation to compose in general. So for the past 2 decades we've been doing it this way, and then 7 years ago Plotkin and Pretner came up with handlers as a way to handle arbitrary computational effects, and this is where our work fits in. So what we are doing here is actually we have an implementation of algebraic effects and handlers in a language called Links, which I'll get to in a moment. And we say that if you want to be truly modular, you need to have an effect system that supports extensible effects. And then we say the abstraction you really want is row polymorphism. And this is exactly what this presentation here is about. Can you read the text, by the way? Yes, good. So in this talk, I will give sort of a brief taster of what programming with row polymorphic algebraic effects and handlers looks like. And in fact, these slides here is maybe quite obvious now. They are a runnable program written in the programming language Links with handlers. So I will show you an example, some examples from these slides here actually running. But I'm skipping over a lot of content. In the paper, you'll find a lot more details. And you'll find quite another example than the one I'm going to do here today. You'll find an example of a game called NIM, which showcases different uses of handlers and goes into quite a detail. You'll find some details about the implementation, so it's based on a novel generalization of a CEK machine. And you'll find all the formalization all there. But for this talk, I'll skip over that. So let's get started here. So what is Links? Links is a functional research programming language meant for web programming. Has a syntax that is looks like JavaScript, but its semantics is nothing like JavaScript. I think it's fair to say. So I appreciate also maybe doing this talk, it will be a bit difficult to read some of the syntax because you'll not be familiar with it, so please do interrupt if there's something, but I'll try to explain it as I go along. So for instance here we have an add function that takes 2 parameters, x and y, and then adds them together. So this is in an uncurried fashion. We can also do it in a curried fashion, so you notice that the differences here have another set of parentheses here. Just to get you a little bit familiar with the syntax. Maybe not so crucial for this talk, but it has 3 different backends. A JavaScript backend for the client side, and an interpreter for the server side. And the server side is what we're going to be working on today. And we have an SQL generator for the database. And especially this last point here is going to come back and bite us in a moment. So we use an effect system to track whether a computation can run in the database, or it can run on the client side or on the server side. Because I should mention, I have built effect handlers on top of Links, retrofitted it in, and that means I also have to live with all this sort of infrastructure that was already in place, and I've tried to retrofit this. So this last point, I'll get back to that in a moment. We'll come back to bite us a little bit. So what is an algebraic effect? Now I've been mentioning that a couple of times. Say an algebraic effect is simply a collection of abstract operations. So for instance, non-determinism can be described as an algebraic effect with a single operation, which is a non-deterministic choose or choice operator called choose. So in Links, you can invoke abstract operations by using a do primitive, which is this primitive here, And I should mention it has absolutely nothing to do with the monadic do from Haskell. It is just an imperative to say, do this now, invoke this thing now. And I should also mention that I don't need to name my effects before I do anything with them. All my operations are structural. So just writing them like this, do choose, is completely legit. So let's try and put this into a context. Say we want to model a coin toss. We might first define a type toss that has two constructors, heads and tails, to nicely model a coin. Then we have a computation here called toss. What we do here is we say if do choose, so our abstract operation from before, then heads, otherwise tails. So far so good. So as you can tell here, I'm just invoking it as is. So the question is sort of what is the type of this computation here? So the sig keyword here allows me to ascribe a type to a computation. So I left a hole here. Let me just click here. So if you look at the context which do choose appears in, we can kind of possibly infer that it needs to be a Boolean, it returns to me, otherwise this is possibly not sound. So let me just write, wrong, like this. So I would expect in my effect signature, so I should maybe make this clear, but the curly braces before the arrow here is my effect signature. So my effect signature lives on the arrows in links. So then the question is this good enough? Well, here I'm actually just saying my computation will perform, or maybe perform choose, but I might be interested in using this in a context where there exist all effects operations. And this is exactly where role polymorphism come into play. So actually our effect signatures and links are implemented using role polymorphism. So what I want to do here, I want to have my pipe and then an effect variable E here. And this effect variable E is a row variable which captures all the operations I haven't mentioned. So this is another way of saying you can invoke this computation in the presence of other operations. Right. So let's try and evaluate this computation toss and see what happens. So boot up links here. Reload the slides. Oops. So I believe I called it example 1. Let's see what happens. Oops. So we get an error back right thrown in our face here. So it says, no, maybe you can read it here. It says on-handle operation choose. Wait a minute, that should be quite obvious. I haven't given any semantics for choose yet. So far we only talked about the syntax of effects and operations. So I need somehow to say what is the meaning of choose. And this is exactly where handlers comes into play. So what is a handler? Well, a handler is really just an interpreter for computations. So you can think of it as a way for transforming a computation that performs some set of effects into another computation that performs another set of effects, or at least have some of these effects instantiated. So I have a basic example here of how we could handle the choose operation. So I declare my handler using the handler keyword, and I call this random result because I intend to give a random interpretation of choose. A handler in general consists of a collection of clauses. This particular example has 2 clauses, namely the return clause and the choose clause. The return clause is always compository. That tells us how to handle the return value of a computation. So the x you see here gets bound to the return value of whatever computation I'm handling. And here I'm doing nothing special with the return value. I'm simply applying the identity transformation. A little bit more interesting is the choose clause here. So it exposes a mysterious parameter resume here. Resume is actually the delimited continuation of the invocation of the operation inside the computation I'm handling. So that is once I actually say do invoke choose, what I do is I suspend my computation, I look for a suitable handler in my context. If I find one, then this continuation resume gets bound to the place where I invoked my operation choose, and then I can invoke the continuation to return control back to the computation where I first invoked the operation. So this is a way to give it an implementation to the operation. And what I'm doing here is I'm simply invoking a function random, which returns me a random number between 0 and 1.0. And then I ask, is this greater than 0.5? So this will give me back true or false, which is exactly what I want for choose. And let's see if this works. So, I believe I call this example 2. Hooray, I got heads back. I got very lucky there. So you see, indeed, I get something sort of random out every time I run it. So what I've just done, I've just applied my handler. I should show that. I've just applied my handler to the computation, TOS, like a function application. And that instantiates the abstract operation inside TOS. All right, let's get to the next one here. I haven't given you the types of handlers yet. So let's try and look at the types. Well, I told you that you could think of it as a handler as a transformation on computations. So we take in some function, some null-array function that has some effect signature E1 here, and then returns me an A. Then I output another computational null-array function with some effect signature E2, and since I don't do anything with the return value, I should expect to get an A back. Now the question is, what should I write in place of these two? Well, this one should be fairly simple, because we have already seen the type of TOS. So this is what I might expect to write. Say, I take a computation that does at least do choose, but may do other effects as well, but I will only handle choose for you, is a way of saying this. So then is the question, what should I output? Well, it's fair to assume that I should do something with choose. And in particular, since I am handling the operation, maybe it's fair to expect that it disappears. So that's why I will put a minus here to denote that the operation is now absent from the computation. You can think of this as it's been instantiated. But we actually also need, because we are using row polymorphism here, I need to mention the same operations, or all the other operations that I haven't mentioned so far. I need to mention them here because due to Remini style. Yes?
So using the row polymorphism, you would just write E, right? So why do you want them? Why do you need the minus there?
The minus. I need to talk about what happens with choose to stay sound, because the E here, this E here mentions all other operations than choose. Yep. Yeah. So if I just put the same one here, then they're no longer mentioning the same set of operations. Does that make sense? I need to say what I'm doing with choose, with the Remini style polymorphism.
Okay.
Yeah? Okay.
The tiny rule for the E says that basically it only describes the bit of the row that doesn't include choose.
Yeah. So this is one type, and this is what you might expect, but we are in the language of links, which already have effects and stuff in it, so you actually need to do something else. I told you that there is a way to tell whether a computation can run on the database or not, and a handler cannot run on the database, so I need to instruct the system that this cannot be done. The way you do that is you use the wild effect, which has a tilde arrow. So this is a wild computation, and this simply means this computation cannot run on the database. So this is just another built-in effect. But it's also to show you that actually the system plays really nicely with the built-in effects of links. So we can save this. Moving on, we can do something else. Yeah, oh sorry. Oh, of random. Okay, I'll show you. So you'll see here it will has some effect row A here. So that means this is syntactic sugar for writing something like this.
Side effects that we don't quite know.
We can instantiate A, depending on the context it's used in. So, does that answer your question? It's yeah. So yes.
That's a mistake.
Yeah, it should actually. I think here it's because the config I'm working with. What it should say something like this is what I would expect it to say because it's a built-in effect. but I think it's because the configuration I'm running with in links at the moment gives a name to all the type variables here, just for the sake of the presentation. So I think this is a bug in links that shows up with this dash a dash. It should show a curly arrow. So just to make clear, this arrow should have shown up. Anyways, it has the wild effect, the random function built in. Let me just get back. Let me just show you another way we could interpret this. We could do an interpretation that enumerates or visits all alternatives in a computation. So how do we do that? Well, I have a handler called all choices here. So it has the effect the signature of all choices is very similar to random result. The difference is the return type here. I return a list of A's now instead of a single A. So what I do is in the return clause, I now do something non-trivial. I lift the return value into a singleton list. Then in my choose clause, I first visit the positive alternative and gathering that result, and that will return me back a list that I concatenate with the outcomes of visiting the negative alternative. So let's try and put this into call this example 3, and indeed we get heads and tails. Those are the two possible outcomes of the Turing course, as we would expect. So moving on, let's make things a little bit more interesting. We have only considered one operation so far, one effect. We can also model exceptions with algebraic effects. It's actually quite straightforward. So how I model exceptions? Well, I don't ever expect to get a return value from an exception. So I will give my exception or my operations the 0 type, so the empty type. And this is how you denote that in links, simply the empty variant type. Because I don't have polymorphism on my effect types, I need to do a few tricks here. I wrap it up in a function here, and then I do the empty I do pattern matching on my operation with the empty clauses because I'm expecting the 0 type to come back, so I cannot possibly give any clause that would match on this. Now we can put this into context here. So here is a drunk coin toss. What might I expect to do in a drunk coin toss? Well, I can either toss the coin and catch it again, or if I'm drunk, I will fail to catch it. So this is what you'll see here. I'm performing to choose between my toss computation from before, which is also an effectful computation, and the fail computation, which I just defined. Now the question is, which type should I give to the drunk toss here? If you're familiar with subtyping, then you might expect me to give it a type that's sort of a super effect type that subsumes both choose and fail. But because of row polymorphism, what I simply do is I take the union of the two branches. So I'll end up with something like this. And of course my effect variable. So I very nicely just get both my operations in here. And I'll skip over this. And I will show you a possible instantiation of this operation by using a maybe handler. So the idea is here, I handle an exception by lifting it to a maybe value. So in the case of success, I give you just the result, and in failure, I give you nothing back. So the last slide here, I have a couple of examples here to show you. So I'll just drag this up so you can see. So if you take, for instance, example 6 here, what I'm doing here is I'm taking my all choices and composing that with the maybe result. So that gives me a list of maybe tosses back. So let's see here. So yep, I get here just heads, just tails, and nothing. So those are exactly the 3 outcomes of toss, drunk toss. Then you can compose the 2 handlers in the opposite direction. So maybe result and all choices. What you then get is something slightly different. You just get nothing back. Because we keep always visiting the failure branch, and since I have wrapped my handler maybe result as the outer handler, then it gets to handle failure, and it would short circuit the computation when it happens, so I never get to return to all choices to visit any of the other branches. And there's an important thing here, that is, the effect signatures are exactly the same. There is no order implied in these effect signatures. Where the difference in semantics come from is the term level. So it's the way I compose my handlers together. It's not the order of my operations that imply the semantics here. And that's sort of the crucial message to get across. And yeah, then just the conclusion here. So I've briefly shown you that the row polymorphism provides a neat abstraction for extensible effects, and also that things compose smoothly. And you can see the paper for further details on the formalism. Thank you.
And now Nick will be the discussant.
Thanks very much for that talk. Actually, I think your talk mirrors quite nicely the way that the paper is presented, and the paper sort of starts with this story about the game NIM, and sort of motivates the use of effect handlers by showing an implementation of NIM where various effects are handled in different kinds of ways. And I like the introduction to the paper because it's a really good introduction to why we're motivated to look into effect handlers at all. So the story being that when we're dealing with effects in a sort of a pure functional language, we're often thinking about how we can be pure, but at the same time deal with an effectful system or effects that might happen in the system. And the traditional way of doing this is you program monadically, and you build up this great big stack of monads, and you're working within that environment, maybe using monad transformers to describe what's going on, and it can get pretty messy pretty quickly. And the reason that we like the effect handlers approach is because it allows you to think about the different kinds of effects in isolation, and it's modular in that sense. So you can do cool things where you can say, well, we've got this syntax tree with various effects, or at least the intention of having various effects in it, and you're going to manipulate that tree in various means until eventually no tree remains. You've kind of handled away all the syntax, and all you have left is kind of the meaning of the program. And the problem with that setup is that it becomes difficult to think about modularity of your effects, or in other words, to give the signature to your effects, and say it in a way that where the signature isn't giving too many hints about the order in which the handlers need to be invoked, right? So that it's kind of a false criticism. Many people say about monad transformers, the problem with monad transformers is that you need to stack your monad transformers in exactly the right order in order for you, and so therefore that kind of dictates what's going to happen. That's not quite true, because you can do the same kind of thing with class constraints, so that you don't have to stack your monad constraints in the right order, so you can make the most of the fact that class constraints are unordered. And so you can play tricks there, but with the approach in effect handlers, you want that to be inherent as well. And this piece of work shows that actually this is really what you want in terms of the modularity of effects. You want to be able to pick and choose what's going on, and I think that shows it very, very nicely. And I guess what I like about this paper is that it's upfront about that fact. It's upfront about the fact that modularity is the key to success here. And it says, okay, rather than just thinking about modularity and how we can fit that into some other language, let's think about what the core of the language should be that provides this kind of modularity. So we look at row polymorphism as being the thing that's required. And so what the paper goes on to describe is row polymorphism as a kind of in a small language of its own right. So that's not links. You've got an actual abstract language that's sitting behind this. And then you give semantics to that, and then you give a semantics to how that's executed on a stack machine again. So I guess it's separating. What I think this paper goes on to do beyond the examples, it separates the notion of what it is to be an effect handler from the idea of, okay, so what's the machinery we need for compositional effects? How do we do that? And I think that's worth looking at if you want to look into the paper some more. One thing that wasn't clear to me from the paper, though, was you started off with. So I think the core of the idea is, you've got this row polymorphism going on, and then you sort of give a semantic to that sort of going downwards. And you show that Link satisfies that with its row polymorphism, because you're using Rami-style polymorphism in the language itself. But what about other languages? Because there are plenty of other languages that also use row polymorphism, or at least can fake it to a certain degree. And I'd like to know things like, is it possible to fake it enough in Haskell, or are we doomed to fail all the time because we can't say something like move minus? Maybe you want to...
Yeah, but I think that's a very interesting question, and that's something we've been asking ourselves a lot also. But as I think this is the way Sam usually explains it, is that you have this big ball of wax where you can do all sorts of things in Haskell, so it's difficult to give like one answer that says, no, you can't do that, or yes, of course you can do that. I think all the encodings that I have seen has some kind of trade-off. So this was sort of a study in how would the clean thing look like, clean from our perspective. What does it look like if you take this as a building thing, and then we build effect handlers on top of that.
Okay. Yeah. So I chose Haskell, and that's sort of a straw man in the sense that Haskell wasn't designed with effect handlers in play. And effect handlers has sprouted up all kinds of different languages like Frank and Shonky and new things. And again, the question would be, how does it relate with all of these things? And obviously, it's difficult because that's the moving target. But again, that must relate to what you're doing.
Oh yeah, sure. So you mean about sort of the effect system of Frank, or the effect system of or the lack of effect system in Shonky, because there is none. I suppose it's another way of doing it. So what they're actually doing in Frank is also some novel form of effect polymorph, row typing, where you just don't have to mention this row variable. So when you program a lot with this, you start noticing that you always have these open effect rows, and it becomes natural to think, maybe I can elide this somehow. Okay. And I think that's what the Frank stuff is doing.
And something else that I thought about, which was you're using links, which at the beginning you said is a language based on sort of web programming and has a database. And I think what you're doing with your effect is all sort of back-end part of that. Could you say a bit more about how? Do you have a vision for web programming in this, or is it just really just the model that you're using, and the web programming is a complete accident?
Yes, yes, there's a vision. I would like to explore web programming with this. I haven't done it, and the reason I haven't done it is because I have not extended the implementation to cover the client side in Links yet. But that is future work. Trying to do, yeah.
Other questions?
So you showed some simple examples, they were nice. What happens if you start putting those things, the effectful computations in data structures? So do you start doing higher rank types and all that, those kinds of things? Or?
No, I haven't had to do anything like that.
We have higher rank types.
Yeah.
So you can do that, yeah.
So when you write type signatures as well?
Yes, but you can get quite far without that,
We
I would
have
say.
more than higher rank types, in fact. I mean, we have full system X. You have to write type annotations if you want to.
Yes.
Follow Nick's lead. I mean, he pointed out different languages that, well, not only Frank and not only Haskell tradition, for example, in Okama, right? It has role polymorphism. It has both unions and products and co-products with role polymorphism. So maybe that's something to investigate, right? So, for example, polymorphic unions in Okama, they have role polymorphism, right?
Yes.
There was a talk in Home this morning. Well, exactly about this. Okay, well, we used Leo Wright's talk.
Oh, sorry.
Just a comment about, row polymorphism. Ben Gaster and Mark Jones wrote a paper about record polymorphism, and it was implemented in the Hugs interpreter like 20 years ago. And it was kind of interesting because they used constraint types constraints to represent row polymorphism. And I think it's just another way you might try to do what you've done. And so they had this constraint, they had this lax constraint. So it's like, some type lax X. And then so you write your program and you get a constraint type, A lax choose, fat arrow like in Haskell and so on. Just
Right.
reminded me of that.
Yes, I will.
It's such an old paper that I'm not sure everyone knows about.
Okay, thank you. I'll check it out.
Any other final questions? Okay, let's thank our speaker again.
Thank you.